How's it going, guys? This is a vector quiz I gave the class some time ago. We'll see if we can go ahead and navigate through this. The points P, Q, and R are shown in the diagram below, and that is true. Okay, find the vector PQ. So what I have is the point P right here. Oops, and this is going to go in the direction of Q. So that is the vector PQ, I'm saying. And to find the actual vector components of PQ, what I'm going to do is take the point Q and subtract the point P. So basically I'm going to take this and subtract this from it and write it as a matrix. So what I'm going to have is 3, which is the x component, minus the x component of P. And then I'm going to have the y component of Q, which is 1, and subtract the y component of P, which is 4. So 3 minus negative 2 is in fact 5, and 1 minus 4 is negative 3. What this basically means is that on the y side, I'm going to go down 3, and I'm going to go over 5. So that's pretty much what that's showing you. Alrighty, so we can scroll down here and continue. Find the vector equation for the line through R that is parallel to line PQ. Okay, well, here we have point R, and they actually give us the coordinates for point R, which is nice. A vector equation of a line, though, has a kind of, well, actually there's an example of it right below us here. So what we have is, this is a good example. The vector equation of a line is given by a point vector and a direction vector, and then the direction vector is multiplied by a scalar. So we're going to have to do that for this. We're going to have to basically say, we could say xy, the position for this line here, for the vector equation for this line. We're going to have a point on this particular line, and it goes through R. So that'll be our point. This is our point vector that we start with, R. And they tell us up here, let me get this cursor moving here, they tell us R is 1 and 6. So we're going to put that right here, 1 and 6. So we have a point vector, and then we're going to add a scalar, which we could call anything. And the IB, they usually call this T, so I'll put a T here. And then we need a direction vector. Now the direction vector could be the same vector. As you can see here, PQ is a vector going in the same direction as our line. And if I had that same vector going on here, PQ, the same thing going on here, if this basically were copied over here, we would basically be creating another line that's actually parallel to this one. And that's what we want, actually, is parallel. So we can actually put the direction vector PQ in here in its place. Because if this vector right here and this vector right here were the same, they would in fact be parallel to each other as such. So let's go on with that. That's the answer here. This is a negative 3, by the way. I don't know what's turning blue on me there. So we have car 1 moves in a straight. This is number 2. So we're going to go to a different question here. All right, car 1 moves in a straight line starting at point A. Its position P seconds after it starts is given by this. Its starting point is 0, 12, and that's our point. They're going to give us a point on our line. This part right here is the direction vector. So we have a point vector and a direction vector, and this together makes a vector equation of a line. P is a scalar, some sort of number, and in this case it represents the number of seconds after the car starts. It's important to keep in mind, though, that this particular thing here, this is kind of like, this direction vector is kind of like your change in x, your delta x, and this is your delta y, which is down here. So it stands to reason then if you turn these upside down, what you'll have is a delta y and a delta x, which is actually your slope, as it turns out. It's going to be negative 3 over 5, the slope of this actual straight line that they're discussing. So that's just a little side note. Find the position vector of the car after 2 seconds. Keep in mind that P represents a second, so they're telling you P is 2. So let's actually find this. We have to find xy the position of the car after 2 seconds. It starts off with at 0:12. That's where it starts. That's its starting point, it says right here. P right here is 2, and then we keep the direction vector 5, -3. This is the same one that I've used here, and it's the same one they give us here. So what this basically means is 0 plus 2 times 5, which we know to be 10. And this was 12 plus 2 times -3, which is 12 minus 6, and that's going to be 6. So the position vector after 2 seconds is given as 10 and 6. Okay, or we could say as a point, let's say that we call this point, I don't know, let's call this point L. No, not L for a line, let's say G. So it's in point G, and that point is 10 and 6. That's basically where the car is after 2 seconds. Okay, let's do the follow-up question here. They're talking about another car, car 2. So let's see here if I can move this. All right. Car 2 moves in a straight line starting at this point. Again, you see this point showing up here. That's the point vector. A point on the line somewhere. It's the starting point. Q is the seconds after the car starts, so here's Q. And this is the direction vector it's going in. It's telling me that these two cars actually collide at some point at point P here. Find the value of P and Q when the collision occurs. Alright, this isn't that difficult. We have a position vector up here for the first car, and we have a position vector here for the second car. And what we need to do if they're going to collide with each other is set these position vectors equal to each other. So I'm going to go ahead and say that 0 plus P times 5, which is 5P, that's going to equal, right here for this one, 14 plus Q times 1, which is 14 plus Q. Alright, and then what I'm going to say here, and for the Y part here, is that 12 plus P times -3, which is 12 minus 3P, equals, I'm not really sure why it turns blue on me, equals 0 plus Q times 3, which is 3Q. So it doesn't show up too well, it's a P. And then we have a system of equations that we have to solve, specifically for P and Q. So let's go ahead and do that. I'm going to solve the top equation for Q. I'm going to subtract 14 from both sides. So when I do that, Q is going to equal 5P minus 14. Alrighty. Now that I have this, I can take this and plug it into this Q right here because it's actually equal to Q. So I'm going to do a little substitution here for the bottom equation. So what I get is 12 minus 3P is in fact equal to 3 times 5P minus 14. And then I'll distribute that, hippity-hoppity distributive property, and we'll solve this equation for P. So 12 minus 3P is equal to 15P, and then 14 times 3, that's 12 and 30, that'll be 42. And then now I'm going to consolidate this. I'm going to basically add 3P to both sides here. Let's just show every step, I suppose. And this will be 18P. And then I'm going to add 42 to both sides. So this will be 0. And I'll add 42. This will give me, let's see here, 54. Alright. And then we'll set this equal to each other. And then we'll divide both sides by 18. Okay, 54 divided by 18. That looks like it'll be 3. Yeah, sure is. 3 times that. Okay. So yeah, that'll be 30 and 24. So that is in fact 3. Now that P is 3, what I'm going to go ahead and see here is this. Q is equal to 5 times P minus 14. P is 3. 5 times 3 is 15. 15 minus 14 is 1. So Q is 1. That's what that's going to be. They asked me to find the values of P and Q, and I did. Here they are. Boom. Alright. I'm guessing we're going to have to use that, though. Find the coordinates of P. Of course, we have to figure out where they collide. Now the good news is we found P and Q. Q is 1, so I'm going to use this equation for the position of car 2. And I'm going to substitute 1 into this little Q right here. So what I'll have is 14 plus 1 times 1. Okay, so 14 plus 1 times 1, and then that will be 15. And then the bottom equation is 0 plus 3 times 1. So 0 plus 3 times 1, which is Q, and that's going to be 3. So your actual position here is 15 and 3. This will work out the same if I scroll up a bit. If I plug in 3 for P, it's going to be 3 times 5, which I know to be 15, and this will be negative 3 times 3, which is negative 9, but we got 12 minus 9, which would be, in fact, 3. So this particular point that you get will be identical to the point that we found down here. So the coordinates of P, we know, is 15 and 3. That's kind of a long-winded explanation, but that's how it works. All right, let's go on to the next question. Consider the points A, B, and D. AD is perpendicular to AB. Find AB. All right. Thought they would never ask. Okay. Again, I find this as point B minus A. Here's B. Here's A. Let's subtract. So I'm going to say 3 minus 1, 1 minus 5, and 2 minus 4. So what I'm going to get are 2, negative 4, and negative 2. That's going to be my vector AB. No problem. All right, let's close this up here. Let's keep going with this. Find AD given your answer in terms of K. This is the same process. We're going to take the ending and subtract the beginning. So we're going to basically do D minus A. And our D right here is 3K and 2. So I'll say, all right, 3K and 2. And we're going to subtract. We're going to subtract A. So it's going to be 1, 5, and 4. And then we got this 3 minus 1 is 2. K minus 5 is what we have. And 2 minus 4 is negative 2. So this right here is AD. Remember, we want it in terms of K, and there is, in fact, a K. So that's your answer for that one. Now they want me to go a step further and show that K is, in fact, equal to 7. This is where it gets a little tricky, and what I'm going to basically utilize is this last bit of information they've given me, AD being perpendicular to AB. As we learned from class, if two vectors are perpendicular, or orthogonal as we call it, their dot product will equal 0. There's a right angle between the two vectors, and their dot product is equal to 0. So basically what I'm going to have to be finding here is the dot product of this vector and this vector, AB and AD. So we're going to go ahead and do that. We're going to basically write it right here. I'll write it down here. It's fine. I'm going to say, okay, we got to find the dot product. So the dot product of AB and AD is given by taking the x components, which is 2 times 2, and multiplying. So I'm just going to write this all out. 2 times 2 plus, up here with negative 4, that's the y component, times k minus 5, plus negative 2 here times the negative 2 down here. So I'll put these in parentheses and figure this out. This is going to be 4. This is going to be negative 4k plus 20. And this is going to be 4 as well. We have 20, 4, and 4. So that's all going to make 28. So it's going to be negative 4k plus 28. Now keep in mind they're telling me that these two vectors are perpendicular. It says so up here. So perpendicular means that the dot product will equal 0. So this in turn should equal 0, and so should this. We're going to solve this equation for k. So basically I'm going to say, all right, that means that 4k is equal to 28. When I rearrange that equation, if I divide both sides by 4, what this is going to in fact tell me is that 28 divided by 4 is 7. So k is in fact equal to 7. And that's what they wanted me to show right here. So that's kind of what I've done. So k is in fact equal to 7 right here. And that's your answer. All Alrighty. Point C is such that the vector BC is equal to half of AD. Alright, so we can go ahead and find the vector BC. They want us to find the actual position vector C, but let's find BC first. Okay, so that's going to be our first step, because they've told me it's half of AD. Well, half of AD, keep in mind AD we know is this vector we found up here. And this is typical for baccalaureate questions. They recycle questions, and you have to use answers from previous questions to answer following questions. So if you get this part wrong, you're probably going to get this part wrong, and then all subsequent questions is pretty evil that way. But since I know k is 7, I can substitute it for here. 7 minus 5 is 2. So let's go ahead and write this vector. Actually, this is going to be 2, 2, and negative 2. That's a negative 2 here. And then we're going to figure this out. Half of 2 is 1. Half of 2 is 1. And half of negative 2 is negative 1. So that's actually my vector BC. We're going to take that vector and use it to find the position vector C. And the way I kind of like to explain this is if I had a graph, if I had some random point basically called A, and another point here, let's see, we're looking for point C. Alright, so this is what I'll do. I actually have, this is what I'm going to do. I'm going to call this, let's just draw through here. This is B, and this is C. And what I have right here in between B and C is a vector called BC. I also have another vector pointing directly to B from the origin 0. So this is called the position vector of B, from 0 to B. We already know the position vector to B because they gave it to us. We know BC now, this vector here, because we have it here. We just found it. If I add this vector to this vector, I'll get a position vector that is pointing directly to C. So this vector plus this vector is equal to this third vector. That's kind of how that works. So what I'm basically having to do is add this vector to the coordinate of B. And if you recall, the coordinate of B is up here, and it's actually 3, 1, and 2. So let's go ahead and find that. I'm going to basically say 3, 1, and 2 plus 1, 1, and negative 1 is in fact the coordinate for C. So 3 plus 1 is 4, 1 plus 1 is 2, and 2 plus negative 1 is 1. So your actual coordinate for C is 4, 2, and 1. That's your answer for that one. And this should be the last question with any luck. Find the cosine of ABC. Alrighty. This is what I like to do if I have a point that I call A, another point that I call B, and a third point which I call C. Although this is actually in 3D space, although I'm not drawing it that way. They want an angle that is given by this middle term here, B. There's an angle here in between two vectors. Now, an appropriate way to do this is if you have this going on here, find the cosine of ABC. I like to imagine the vectors leaving this central angle here. If B is where the angle is, I like to imagine vectors leaving the angle. And then what I, in a sense, have is the vector AB and the vectors BC. So I'd actually would like to find the cross product. Actually, this is not AB, this is BA, we should say. So I would actually like to find the cross product of BA and BC. And I'll explain to you why we're doing BA instead of AB in just a second. But let's go ahead and figure this out here. BA is actually the same thing as AB, except we're flipping all the signs in the vector. We're multiplying everything by -1 and putting it in the opposite direction. So that's what we're doing. Let's go back in here and recall that AB is in fact 2, -4, and -2. So if I flip these, I can actually declare that BA is the same thing but everything flipped. So I have a -2, 4, and 2 here. And that's what I'm going to use to answer this question. -2, 4, and 2. So I have a -2, a 4, and a 2 for this. And I know BC we already found up here is 1, 1, and -1. We'll take a dot product. 1, 1, -1, and then we go from there. So I have -2 times 1, top and top. That's going to give me -2. I got 4 times 1, which is 4. and then I got 2 times -1, which is -2. As it turns out, when you add these together, this is actually going to equal 0. What that means about this angle right here that they're telling me is in fact it's 90 degrees. And that means these two vectors are orthogonal. If we recall the dot product formula, it's a vector A dot product with vector B. That'll equal the magnitude of vector A times the magnitude of vector B times the cosine of the angle between them. I have now found this particular dot product. This is actually equal to 0, I've discovered. So this part is 0. A and B are both non-zero vectors. We can see that. Here's one and here's the other, A and B. Because they're not 0, these are actually going to have some sort of magnitude that's non-zero. So the only way we can multiply two non-zero magnitudes by something else and get 0 is if this something else, being the cosine theta, is in fact equal to 0 itself, because these will not be 0. So cosine theta actually has to equal 0 for this to actually make any sense. And of course, as we know, the cosine theta, the theta itself is actually called angle ABC. So we're going to call cosine of angle ABC, this is in fact equal to 0. They want me to find that, and that's actually what the answer is. It's actually equal to 0. It doesn't actually ask me to find the angle itself, although I did, because we know if that dot product is 0, this is actually 90. Now let's go back to this discussion about where this vector is going. I wanted vector BA because if I had vector AB, I'm basically looking at a vector that's going in this direction. And then what I'll find here is this angle instead. As it turns out, for this particular situation, this is also 90, and they'll be the same. But that doesn't happen all the time. If I want this very specific angle, I need to use the vector BA. That's just a little food for thought for you. So here's the answer to this question. I know it's kind of long-winded, but hopefully that helps you out. Most people did pretty well on this, considering we discussed it in class. So I appreciate you watching, and hopefully you got something out of that.